Hello again. Today I will tell you about cryptographic combiners. In the previous lecture, we discussed two notions of hybrid security. One to achieve backwards compatibility and the second to achieve stronger security guarantees. Today's lecture will deal with a cryptographic tool to achieve the second notion. A combiner combines two cryptographic schemes S1 and S2 in such a way that an adversary attacking the combined scheme would have to break both underlying schemes. In other words, the combined scheme S is as secure as the strongest of the underlying schemes. You can think of, for example, combining a classical scheme, here depicted in green, with a post-quantum scheme, here depicted in blue, with an atom into one that has both the trust of the well-studied classical scheme as well as the post-quantum security of the new post-quantum scheme. S is then also called a hybrid scheme. But how do we build such a combiner? First, let's look at combiners for signature schemes. Recall that a signature scheme allows a user to sign a message with their secret key, and others can verify the signature with the same user's public verification key. In these slides, I will denote signatures with a squiggly line and a pen, and a verification with a magnifying glass. Our first signature combiner is very simple. It merely signs the message with both schemes, and the verification also checks both signatures. As the signatures are concatenated, this is called the concatenation combiner. It is easy to see that an adversary that would want to forge a signature for this combined scheme needs to forge a signature for either of the underlying schemes, and thus would have to break the unforgeability of both underlying schemes at the same time. This simple combiner is sufficient for typical applications. However, the signatures can be separated and presented individually, which is sometimes seen as a downside. A second way to combine two signature schemes is the following. First, we sign the message with the first signature scheme, and then we sign the message and the first signature again with the second signature scheme. Verification again checks both signatures with the corresponding verification keys. An adversary that wants to break this combined scheme would have to forge both the signature of the first scheme on the message, as well as a signature of the second scheme on the message and the first signature. Note that this is not enough to just sign the first signature with the second scheme, as in this case, the adversary could reuse the second signature if the first scheme is broken in such a way that many messages have the same signature, even without forging a signature for the second scheme. Next up, I want to discuss the options for combiners for key encapsulation mechanisms. First, what is a key encapsulation mechanism, or KEM for short? A KEM is a way to exchange a symmetric key between users that only know each other's public key. To send a message to Bob, Alice runs the encapsulation algorithm E on Bob's public key, here depicted as a lock. This algorithm outputs a symmetric key, here depicted in red, as well as a ciphertext encapsulating the symmetric key, here depicted as a box that is locked with Bob's public key. Alice then uses the symmetric key to encrypt the actual message with a symmetric cipher, for example AES. She sends the AES ciphertext along with the encapsulated key to Bob. Bob can then decapsulate the symmetric key with his secret key and decrypt the AES ciphertext using the symmetric key. So now the question is, how can we combine two KEMs? The setting is that Alice first runs the encapsulation algorithm of both schemes, resulting in two symmetric keys and their corresponding encapsulation. One natural approach would be similar to the nested signature combiner, where one first decrypts the message with one key and then the ciphertext again with the other. However, this approach has many drawbacks. For example, having to run the symmetric encryption algorithm twice. A second attempt could be to compute the XOR of the two keys to obtain the final key. However, this is not secure against chosen ciphertext attacks, as the adversary may manipulate the symmetric key encapsulated in the weaker scheme. Therefore, a more sophisticated key derivation function is necessary rather than a simple XOR. It is known that it is possible to derive the combined key by applying a so-called split key pseudorandom function to the two keys and the concatenation of the two ciphertexts. Such a pseudorandom function takes as input two keys, and it is secure. That means the output is indistinguishable from random if either one of the keys is secretly chosen at random. This is the case if either one of the underlying chems is secure. There are different variants of constructing such PRFs, usually by nesting PRFs and dual PRFs. Dual PRFs are indistinguishable from random when at least one of the inputs, the key or the message, are chosen at random. A popular choice for a dual PRF candidate is the HMAC. However, this is unproven. There exist less efficient but provably secure instantiations of dual PRFs. Let's summarize today's lecture. We saw combiners for digital signature schemes. These are simple constructions and easy to understand. Usually it suffices to use the concatenation of the two signatures, and the main challenge is key management of the two keys. This will be discussed in a later lecture. On the other hand, combiners for key encapsulation mechanisms are a bit harder to achieve. While there are some positive results in constructions, more research in the area is still needed to close the gap between theory and practice so that we can have constructions that are both efficient in practice, but also stand on solid ground from a theoretical perspective. That's it for today's lecture. Thank you very much for your attention.